Hi there, this is Truth Socrates. Welcome to a brand new video series, and this one is about infinite sequences and series. So we are starting a new series, no pun intended, because I'm excited to let you know that we have a textbook for this part of our class, a textbook that I've been working on for the last couple of years. And it's all about infinite sequences and series. I also wanted to reach a wider audience, hopefully, so those from other schools, other colleges, who are taking a calculus class that specializes in infinite sequences and series will be able to make use of this video, hopefully learn from it and help them out in their classes. So I'm about to show you the book, but to prepare ourselves for what we're going to do today, let me tell you what we are going to cover. We will cover the first two sections of part one. I have decided to label my sections alphabetically instead of numerically. So we will cover sections 1A and 1B. In section 1A, we will define what is an infinite sequence, and this is the notation for an infinite sequence. We will go to GeoGebra and we will learn the sequence command, which will enable us to graph a sequence. Very similar to the graph of a function, but they're just points. We'll talk about the limit of a convergent sequence and how to use familiar limit laws to you that tell us how to find the limit of a convergent sequence. Then we'll go on to section 1B, where we will dig a little bit more. In 1A, we only talk about convergent sequences, but there are, of course, divergent sequences. So we will see that there are a total of 4 kinds of sequence. Some are convergent, and there are 3 kinds of divergences. We'll talk about geometric sequences, and we'll see that they basically fall into one of these 4 categories. So that's a good reason why we talk about geometric sequences in the context of these 4 kinds of sequences. And then we will put convergent sequences together and see how we can use limit laws and some algebra in order to find their limits. All right, here we go. This is the cover page of my textbook. Here is a diagram. This is called the Mandelbrot set. And some of you are familiar with fractals, and that is, of course, an example of a fractal. And fractals are actually constructed using the concept of an infinite sequence. So I thought, okay, I'm going to steal this from the internet, and it'll make a good cover and related to our material, of course. So here's our table of contents for this OER. Our video will be about section 1A and 1B, Introduction to Infinite Sequences, and 4 kinds of sequences, because there are 3 kinds of divergent sequences. In the next video, we will talk about recursive sequences and the monotone convergence theorem, coming real soon. Now, the bulk of infinite sequences and series talks about the concept of an infinite series. So we will talk about 7 tests that will allow us to decide whether an infinite series is convergent or divergent. So here they are: divergence test, integral test, ordinary comparison test, limit comparison test, the alternating series test, and the root and the ratio tests. Along the way, we'll talk about 2 different kinds of convergence for infinite series and why they are different from each other. All right, and later on, we'll talk about how we can use infinite series in order to create what are called representations of some familiar functions in calculus, such as trig functions, sine and cosine, and the exponential functions and logarithmic functions. So that will be coming a little bit later. For those of you who are in my class, what we are doing today is the beginning of the third unit, the third module in our class. And this concept, power series and Taylor series, will be the beginning of the fourth module in our class. All right, so here's the definition of what an infinite sequence is. It's basically just a list of numbers. And this is the notation that we'll use just to begin with. We have curly braces here and a letter to represent the name of the sequence and a subscript, n. So this is pronounced, of course, a sub n. And n will go from 0 to infinity. In the intro, I said, well, we can start the sequence at k. I had the symbol n equals k at the beginning of our video. And that's because 0 is basically an artificial beginning. Okay, you can start a sequence at 2 or even at -3. But of course, a lot of times we'll be starting at 0 or 1, a very low number. So we call a sub n the nth term of our sequence. And because it's a list of numbers, we can actually explicitly list out the numbers, right? We will have a sub 0, a sub 1, a sub 2, and so on. Okay, so at the bottom, you see an example of a sequence which is defined as a function. Let's go to our workroom and I'll give you another example, a different example. I do encourage you to read the examples in our textbook. All right, so here's a brand new example for you. Let a sub n be -9n plus 5 all over 12n minus 7. And we'll start our sequence at 0. Does it have to be 0? No, of course not. We can start at 1 or 2 or even a negative number, because the only time that the denominator is 0 occurs when n is 7 over 12. But 7 over 12 is not an integer. It's not a whole number. So we can actually start the sequence at any number, any integer that we want. All right. So let's compute the first few terms. So we start with a sub 0. We simply plug in the number 0 into our function. So we get 0 plus 5, 0 over 0 minus 7, -7. So we will just get 5 over -7, or if you want, you can write it as -5 over 7. All right, what is a sub 1? Now we plug in 1, and we will get -9 plus 5, so that's -4 divided by 12 minus 7, so 5. So we will get -4/5. All right, I'll just write it that way. What is a sub 2? So we are going to get -18 plus 5, that is -13, divided by, and it's 24 minus 7, so that is 17. -13 over 17. Okay, one more. A sub 3 is, n is 3, -27 plus 5, that's -22, divided by 3. 36 minus 7 is 29. All right. So these are the 0th term, first term, second term, and third term of our sequence. So notice I said 0th, even though you might say, isn't that the first term? Isn't that the first number that we see? To avoid confusion, we will refer to the index, the value of the index, to label the term. Okay, so we will call this the 0th term, first term, second term, third term, and so on. All right, we are going to hop on now to GeoGebra so that we can visualize the sequence. All right, here we are in GeoGebra. So the basic syntax for the basic command that we will use to study sequences is, of course, the sequence command. And let me introduce it to you this way. You will start with a formula for the sequence, and I'm just going to put n there instead of what we had earlier. We'll change that in a little bit. After the formula, you will declare the index name, which is n, and starting value, let's use 0, ending value 10. Woohoo! So this is a simple kind of sequence. The formula is just n, and of course, it basically just lists out the numbers from 0 to 10. All right? Now, actually, that is not the simplest kind of sequence. Let's duplicate input. The simplest kind of sequence would be a constant sequence. So if it's always 3, then you're going to get 3, 3, 3, 3, very, very boring, of course. So let us actually type in the sequence that we were talking about. We have negative 9n plus 5, negative 9n plus 5, and then we will divide by 12n minus 7. All right, so as you can see, GeoGebra is providing decimal approximations. We got exact fractions, rational numbers in our computations, okay? Because, you know, n is an integer, so we can easily express the terms as exact rational numbers. Now, we want to graph the sequence. So what we can do is we will duplicate this command. We will create points. So we are going to wrap the function in parentheses. That will be the y-coordinate. The x-coordinate is simply going to be n. Okay, there you go. Okay, so x-coordinate is n, y-coordinate is a sub n. So when n is 1, we get negative 0.71. I'm sorry, when n is 0, we get negative 0.71. When n is 1, we get negative 4/5, negative 0.8. When n is 2, we get this, and so on. So we can see, let me hide this a little bit. This is the graph that we are getting. Okay, so the terms go from 0 to 10. And you're hopefully saying, wait a minute, they are almost the same. But are they actually the same? Well, close. But if we add more decimal places to in our settings, we're going to get certainly differences even in later decimal places. Okay, so guess what? The key concept when we're talking about infinite sequences and series is the concept of a limit. All right, so in the textbook, I show you how you can change the appearance of our sequence by changing the size of the points. So you can find that in the Style tab of that sequence object. So to prepare ourselves to define the limit of a sequence, let's review what the limit of a function is as we go to infinity. So we have seen this symbol before in previous videos. Remember, we talked about horizontal asymptotes for exponential functions. So in general, if you have a function which is defined from some number a onwards to infinity, we will say that the function has limit L as x goes to infinity, written as limit as x goes to infinity of f of x equals L, if, using notation from basic calculus, for every positive number epsilon, no matter how small, we can find a positive number n, so that if x is greater than capital N, then the absolute value of f of x minus L is less than epsilon. In this case, we call y equals L a horizontal asymptote for our function. So you've seen this in calculus. Let's review it in GeoGebra. All right, back to our sequence. And you know what? Let me show you how to use the settings command so that, oh, look, there's style over here. Yeah, good, you can see it. We can reduce the point size to 4 or 3, make it smaller. And we can change the color. Okay, we can make it red, my favorite color. And there we go. Once you click on the screen, you can see the result of the changes that we made. Now, horizontal asymptotes and functions, and limit of a function. This sequence obviously comes from a rational function. So we can write f of x equals, parenthesis, negative 9x plus 5 divided by, okay, so check it out, GeoGebra is starting to graph, divided by 12x minus 7. Ooh, okay, so as we can see, the points on our sequence lie on that function, of course, because our sequence is simply the value of our function at integer points, positive integer points. And if we keep going further to the right, well, our sequence will again land on the graph of our function. And check it out, our function almost looks like a straight line, even though it is obviously not a straight line. Well, you know how to do this. We did this in L'Hopital's rule. We did this all the way back in basic calculus. To find the limit of this function, using first principles, we can multiply and divide the numerator and denominator by 1 over x. So we'll get negative 9 plus 5 over x over 12 minus 7 over x. The limit is negative 9 over 12. So we have a horizontal asymptote, y equals negative 9 over 12. And I don't see it. Well, that's because the sequence is practically on top of that horizontal asymptote. Let's hide the graph of f of x. Okay, there you go. F of x is gone. This is now just the line. But as you can see, some terms are quite distinguishable from that line. Okay, if we zoom in, yeah, you can definitely see some separation between the points and the line. But the points are definitely very, very close to that line. So the definition of the limit talks about epsilon and n. So let's talk about that for just a couple of minutes. Let's make epsilon 0.1. So we want our function to be between this limit plus epsilon and the limit minus epsilon. So we will have minus 9 over 12, minus 9 over 12 plus 0.1. That is our upper horizontal line. And below we will have y equals negative 9 over 12 minus 0.1. There you go. So as you can see, it doesn't take long for our function to be within this epsilon strip. I hope you remember that notation. In fact, for this epsilon, from the beginning, our sequence, our function, let's bring back our function. Our function is, it takes a while, not much, not far. From a little below 1 onwards, your function is within that epsilon strip. Okay, what if we make the strip narrower? So plus 0.01 minus 0.01. So our strips are a lot closer to each other, and we need to zoom in because right now at 2 we're still outside the strip, still outside. And then are we inside yet? Are we inside yet? It looks like there you go. At 3, we are now within our epsilon strip. So basically, we're going to use this same idea to talk about the limit of a sequence. All right, so this is patterned just like our limit for a function. We will say that an infinite sequence converges to a limit L if for every positive number epsilon, no matter how small, we can find a positive number n, so that if little n is bigger than capital N, then the absolute value of a sub n minus L is smaller than epsilon. This means that the distance from a sub n to L is smaller than epsilon. Or, in other words, the term a sub n is within the epsilon strip around y equals L, which is bounded by epsilon plus L and L minus epsilon. So we will write this as limit as n approaches infinity of a sub n is L, or a sub n arrow L. So a sub n approaches L. That is how we pronounce the arrow symbol, or a sub n converges to L. So we will say in this case that a sub n is a convergent sequence and y equals L is a horizontal asymptote for the sequence. So while we're here, we might as well look at the example in our textbook, where we have, instead of our minus 9n plus 5 and so on, we have 6n plus 5 over 9n minus 4. So using the same idea, the limit is 6 over 9, or 2/3. So we want an epsilon, we want an n so that a sub n minus the limit is less than epsilon for any possible value of epsilon. So we demonstrate in this diagram what happens if epsilon is 0.2. Okay, so in our GeoGebra, we looked at 0.1 and then 0.01. So in this diagram, we have 0.2. So here is the parent function, which is in this case 6x plus 5 over 9x minus 4. We can see the points on our sequence, the integer values. And if you go past, it looks like 4 or 5. Once you cross that point, your sequence is within that epsilon strip. So the definition says, no matter how narrow we make that epsilon strip, you can still find a cutoff point, basically. Once you go past that cutoff point for n, you will be within that epsilon strip. All right, in some of our past videos, we spent a lot of time learning how to find the limit of a function using, let's say, L'Hopital's rule. So if our sequence comes from such a function, like in our example, we have minus 9x plus 5 over 12x minus 7, and if we know that that function, that parent function, has a limit at infinity, then it is also the limit of the sequence which we extract from that parent function. So in particular, there are, of course, very famous families of sequences, and we did this constant sequence in our GeoGebra example. We saw functions of this form when we talked about improper integrals a couple of videos ago. So in the same way, if you change the power of x to any positive number, all of these will have limit of 0 as n goes to infinity. As n gets bigger and bigger, n is in the denominator of this fraction, and the power of n in the denominator is a positive number. So as n gets bigger and bigger, that power also gets bigger and bigger. Even though it's square root of n, that still goes to infinity. And so the reciprocal, 1 over n to the p, has limit of 0. All right, here are some fresh examples for you. 3 of them. All of them involving the natural logarithm function, one of my favorites. So suppose we have a sub n is ln of n squared plus 1 over n. We can't divide by 0, so we'll start the sequence at 1. Okay, so what's the limit of the sequence? Well, it's not very obvious. As n gets bigger and bigger, n squared plus 1 gets bigger and bigger, ln of n squared plus 1 also gets bigger and bigger, and n gets bigger and bigger. So do you see what I see? This quotient is an indeterminate form. Of the form, no redundancy intended, well, bigger and bigger, bigger and bigger, so that has the form infinity over infinity. So, shall we apply L'Hopital's rule? So by L'Hopital, we can try to get this limit. This approaches, where's my right arrow? There you are. This approaches the derivative of the numerator, so that's ln, so that becomes 1 over n squared plus 1 times the derivative of the numerator, which is 2n, and then the derivative of the denominator n is simply 1. Okay, so is that still infinity over? Well, actually, yes. If you simplify it, that 1 just goes away. So this is simply 2n over n squared plus 1, which is still infinity over infinity. Yeah, I'm not going to lie to you. So we can try L'Hopital's rule again. That approaches the derivative of the numerator is now just 2. And in the denominator, we see 2n again. And now we can see that's no longer infinity over infinity. That's 2 over infinity. So that limit is 0. All right, so the sequence demonstrates how we can use L'Hopital's rule to find the value of a sequence. Follow up. So this time, let us move the ln of n squared plus 1 to the denominator. And again, we can't divide by 0, but oh, can this be 0? Ln of 1 is 0, but since we start at 1, we'll start with 2 inside the ln, so we're not dividing by 0. We're safe. So what is this limit? Well, this has limit 0, so maybe this has limit 0 also. So let's think about that. If we ignore that ln of n squared plus 1, we'll just get 1 over n. Okay? But we know we were just talking about 1 over x to the p. We know that 1 over n goes to 0. Okay? So this term, well, it's always positive. Ln of 2 is positive, ln of 3 is positive. So this term is positive, and it is smaller than 1 over n. So I have a 1 over n I can steal. I'll steal u, and I will turn that into 1 over n. Okay, so whatever this is, it's positive, and this thing is bigger than 1, so we're making the 1 over n smaller by including that. So 1 over n is bigger than the terms of our sequence. And I hope this rings a bell. The left side is 0. The right side is 1 over n, which goes to 0. So our term, thus our sequence, also goes to 0 by the squeeze theorem. All right. The left side is always 0, so its limit is 0. The right side has limit 0, so what's in between must also have limit 0. All right, cool. How about this one? Remember this? What happens as n goes to infinity? Well, can we start at 0? Yeah, you'll get 1. 5, sure. Ln of 5, that's a real number. When n is 1, 8 over 3, sure, that's fine. That's a real number. Okay, and we're not dividing by 0 because negative 1/2 is not an integer. So we're safe. Okay, so how can we find this limit as n goes to infinity? Well, let's work from the inside. Okay, 3n plus 5 over 2n plus 1, that's a lot like our first example. And the limit is simply 3/2. Okay, so that goes to 3 over 2. And if you forgot how to do that, there's always L'Hopital's rule. Our limit is 3/2. So by continuity, our sequence ln of 3n plus 5 over 2n plus 1, that should have limit ln of 3 over 2. Whoops, just this one, ln of 3 over 2. There you go, which is a small positive number, right? ln of 1.5. Okay, so those are our 3 examples for finding the limit of more sequences. Let's move on now to section 1b, where we talk about convergent and divergent sequences. Okay, so everything that we have seen so far are convergent sequences, but we'll see examples where there is no limit, or maybe the limit is infinity or negative infinity. Let's go back to GeoGebra. All right, so here's a fresh GeoGebra screen. What we're going to do is we're going to review some exponential functions that we saw in earlier videos. So let's start with the exponential function 3/5 to the power x. Ooh, okay, so there it is. So 3/5 is smaller than 1. So our exponential function is decreasing. Okay, so what happens when we flip that? If we have 5/3 to the power x, ooh, now we have an increasing function. Okay, so by the same token, we can turn these functions into sequences just like we did in our earlier examples by replacing x with an integer, a positive integer. Well, we can even start at 0 and we will get 1. So in fact, because our functions are defined for all real numbers, we can start at any integer that we want. All right, so maybe let's hide them for now, and then let us now make a sequence. So let's go straight to the graph, shall we? So let's input sequence, sequence, and we have 3/5 to the n, comma, n, comma, 0 to 10. Okay, there you go. So here is 3/5 to the 0, it's 1. 3/5 to the first power is 0.6. 3/5 squared is 9 over 25, or 0.36, and so on. Let's plot them. So let's make a point, parenthesis, n, comma. Okay, there they are. So here are the dots, and I'm not going to waste time by making the dots smaller. We know that 3/5 to the x has the x-axis as a horizontal asymptote. So therefore, this sequence has also the x-axis as a horizontal asymptote. In other words, its limit is 0. Okay, so this is an example of what is called a geometric sequence. In part 2 of our textbook, we're going to find the infinite series corresponding to this, which is called a geometric series. We're going to add them up, and we're going to see that the sums, what are called the partial sums, do converge to a limit. More on that later. So in the same way, we can look at the terms of this sequence if we turn this function into a sequence. So let us duplicate input, and instead of 3/5, let's do 5/3. 5 over 3. Ooh, okay. So check it out. The terms of this second sequence are, of course, just getting bigger and bigger. Crazy. So yeah, are they getting closer and closer to some number? No, I don't think so. We've seen this behavior before, especially when we did indeterminate forms and so on. So we can say that this sequence will diverge to infinity. Okay, so the value of the terms will get bigger and bigger without bound. Okay, now when we did exponential functions, the basis had to be positive. We can't have negative 3/5 to the power x. Should we dare? I'm going to make it appear again. If I put a minus sign here, disappeared because GeoGebra doesn't like that. The base has to be a positive number. But here's the thing. If we look at a sequence instead of a function defined on all reals, can this be negative 3/5? Negative 3/5 to the 0, still 1. Negative 3/5 to the first power, negative 3/5. Negative 3/5 squared, sure, 9/25. Negative 3/5 cubed, sure, negative 27/125. So, GeoGebra has no problem if we turn 3/5 into negative 3/5. So I'm going to put a negative here, minus 3/5, and ooh, they suddenly appear. So I'm going to, what are we going to hide? Let's hide this sequence that diverges to infinity, and let's hide this as well, okay? So this is now only negative 3/5 to the n. So as you can see, sometimes it's positive, sometimes it's negative. So this is an example of what is called an alternating sequence. Alternating because it goes positive, negative, positive, negative, positive, negative, and so on. Okay? In fact, it's predictable. The even terms, when n is 0 or 2, 4, 6, when you raise a negative number to an even integer, you get a positive number. Conversely, if n is odd, negative number to an odd integer will give you a negative number. But is the limit still 0? Sure. Now we can think about the squeeze theorem, because the terms are either 3/5 to the n or the negative of 3/5 to the x, I should say. Okay, so there are two functions going on here. So let's go back here and remove that offending negative sign. So that's one function. The points on our sequence are on that function. The other points are on the negative of that graph. So I'm going to duplicate this, and then I will put a negative in front of that function. Boom. Ooh, different color. So the sequence is either on 3/5 to the x or negative quantity 3/5 to the x. Okay, you can't put the negative inside. It has to be outside of the exponential function. So of course, both of these have limit 0, since the original is limit 0. The negative also has limit 0. So by the squeeze theorem, the terms of our sequence also converge to 0. Awesome. So now, what's our last example for this? So let's hide these. Okay, we're going to go back to 5/3 to the x. Okay, 5/3 to the n, rather. So it was perfectly fine for us to put negative 3/5 instead of positive 3/5 as the terms of our sequence. So there is nothing wrong either for making 5/3 negative 5/3. Okay, so I'm going to put a negative here, a minus 5/3, and ooh, check it out. So this time, oh my goodness, what is happening here? Again, it's alternating. So the positive, the even powers are positive, the odd powers are negative. Okay, but now it looks like the positive terms are getting bigger and bigger in absolute value without bound. The negatives are doing the same thing, except the absolute values are getting bigger, but the sign, of course, is negative. So does this diverge to infinity? Well, these diverge to infinity, these diverge to negative infinity, but they're all part of one sequence. Okay, so that one sequence does not diverge to infinity or negative infinity. We will say that that really bad sequence simply diverges. All right, so let's formalize and recap what we saw in GeoGebra. We played with exponential functions. and we turn the exponent into an integer. And instead of writing a to the x, okay, we are going to write r to the n, because this is the notation that we will use when we talk about geometric series. So r is a real number. It can't be 0. Yeah, we don't want 0 to the x now, do we? 1 to the x, that's always 1. Okay, so we will not allow r to be 0 or 1. It's called the common ratio of the geometric sequence. So the sequence r to the n is called a geometric sequence. So we did 3/5 to the n, 5/3 to the n, negative 3/5 to the n, and negative 5/3 to the n. So from there, we saw that sometimes the sequence converges, sometimes it diverges to infinity, and sometimes it simply diverges. So we are going to use those to define 4 kinds of infinite sequences. Only one kind is going to converge. So the best kind, we have convergent sequences where the limit is some real number L. We have sequences that diverge to positive infinity, meaning the terms get bigger and bigger without bound as n gets bigger and bigger. There are sequences that diverge to negative infinity. So the terms get bigger and bigger in absolute value, but they're always negative. So we will say that our sequence diverges to negative infinity. And then there are some, like negative 5/3 to the n, where you have a positive big number followed by a negative big number. It's just crazy. So in this case, we will say that our sequence simply diverges, or the limit does not exist. In the case where the limit is infinity, we will still say that the limit exists, but is infinite or negative infinity. All right, so let's generalize. So we saw that 3/5, the 0, negative 3/5 by squeeze also goes to 0. So 3/5, negative 3/5, they go to 0 because our base, our common ratio r, is between 0 and 1 in absolute value. 5/3 is bigger than 1. So when our r is bigger than 1, then our geometric sequence will go to infinity, just like 5/3 to the n. Negative 5/3, it does crazy things. So when it does that, when r is smaller than negative 1, or equal to negative 1, okay, because minus 1 to the n, you're going to get minus 1 plus 1 minus 1 plus 1. They don't go to infinity, but they don't approach a specific number either. So in that case, our geometric sequence also diverges. All right, so when we know that 2 sequences converge, then we can actually combine them. Suppose that we had 2 sequences a sub n and b sub n. A sub n has limit L and b sub n has limit n. Then we can combine them using arithmetic. The limit of an plus bn is L plus m, the sum of the limits. The limit of an minus bn is L minus m. The limit of the product, an times bn, is L times n. The limit of the quotient is L divided by m, but of course we cannot allow m to be 0. Never ever. If a sub n happens to be a constant sequence, then the limit of c times b sub n is simply c times m. So this allows us to combine convergent sequences using addition, subtraction, multiplication, and division, as long as we're not dividing by 0. So let's go back to our workroom and combine some of the sequences that we saw earlier. Okay, well, 0 is a boring number and you can't divide by 0. So let's take these 2 examples. This is one of the last ones that we did. And we started out with this example at the beginning of the video. So for this ln, we know that the inside goes to 3/2. So the sequence with the ln converges to ln of 3/2. This sequence we know has limit -9/12 or -3/4. Okay, so if we simply divided these two sequences, again, we're not dividing by 0. That only becomes 0 when n is 5/9, not an integer. We are safe. So the limit of that sequence, which is a quotient of our two examples, is simply the quotient of the two limits. So for the numerator, the limit is ln of 3/2. So that is the limit of our numerator. And for the denominator, the quotient is -3/4. So that is the limit of our denominator. And of course, if you want to simplify, we can write this as -4/3 times ln of 3/2. Oops. There you go. So that is the limit of the quotient of those two sequences. Now, to end this video, we are going to look at two sequences which are related to each other. So we can start the first one, a sub n, and that should be lowercase. There we go. Sine of n. All right, so we know sine of x, right? This is sine of n. So basically that means sine of 0, which is of course 0, and then sine of 1. And maybe you're like, wait, 1 degree? What is that 1? 1 radian, okay? You're used to things like angles like pi/4, pi/6, and so on, okay? So pi/4 is about 0.7 something, okay? So this is sine 1. And Maple, could you, sine of 1 radian is approximately 0.8. So what about 2? What about 2 radians? Sine of 2 radians is, we're now in the second quadrant, so the sign is still positive. Sine of 2 radians, 0.9. All right, so let's do a couple more. What about sine of 3 radians? Still in the second quadrant, so we're going to get 0.14. And now sine of 4 radians, we're now we've gone past pi. We're now in the third quadrant. So that's negative. Okay, so something weird is going on here. Let's go to GeoGebra and we'll come back to talk about the second sequence. All right, so here's another fresh GeoGebra screen. So yeah, you know what? Let's start with just the sine function. F of x equals sine of x. Okay, so everybody knows what that looks like. And now let's plot sine of n from 0 to 10. Let's see what's going on. So sequence, and we will have from 0 to 10. But instead of n, we will have sine of n. Let's delete sine of n. Okay, so there's our sequence, but I want points. So let us plot parenthesis n comma sine of n. There they are. Okay, so sine 0 is 0, sine 1, 2, 3, sine 4 is negative, 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 positive, positive, positive. So it looks like, yeah, it's going to go up and down, up and down. Let's go up to 20. So it looks like, 3 positives, 3 negatives, 3 positives, 3 negatives. Let's keep going some more. Let's go all the way up to 40. Check it out. So this point is either positive or negative. Sine 22. What is sine of 22? Oops. This is the annoying thing about GeoGebra. The default angle measurement is in radians. So the quickest way to turn that into radians is simply multiply by pi over 180. And what did we get? Can be so annoying sometimes. So what I did was I just put 0.0 in front of the 22, and that forced GeoGebra to accept it as a radians. So it's a negative number, a small negative number. So we have positive, 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 negative, 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 negative. Okay? So we thought, oh, it's just 3 positives and then 3 negatives. But no, you can't really tell that you will always have 3 positives and 3 negatives. You could have 4 negatives here, and nothing is stopping us from having 4 consecutive positive values either, even though we don't see one right now. So this is a very bad kind of sequence. Okay, sometimes it's positive, sometimes it's negative. So can the limit exist? Absolutely not. Okay, because the limit can't be positive because we have lots of terms which are negative. The limit can't be negative either. 0 could be a problem. Okay, but we can also argue that you can always find terms which are close to the absolute maximum of 1 in our sequence. Okay, so 0 cannot be the limit of our sequence either. So this sequence obviously diverges. Not to infinity, not to negative infinity. Simply diverges. So we are now going to look at the second question, which is what happens if you divide this by n? All right, so let's just write down our conclusion from GeoGebra. So this sequence simply diverges. All right, so our second sequence is sine n over n. We already know that sine n diverges. Okay, so we cannot apply directly the limit laws like we did when we saw 2 convergent sequences in our last example, and all we had to do was divide the limits of those 2 sequences. Okay, so we need something a little bit deeper here, but it's actually something that we already saw. All right, so what do we know about sine n? Well, it does crazy things, but it still lies on the sine wave. So sine n is between -1 and +1. So where are you? There we go, less than or equal to sine of n and less than or equal to 1. Okay, so we can divide all the terms in this inequality by n because n is a positive number. When you divide or multiply inequalities by a positive number, you don't have to reverse the sense of the inequalities. Okay, so we can copy that and we will turn them all into fractions. So that we'll get -1 over n, and in the middle we will get sine of n over n, and on the right side we will get 1 over n. Okay, so you know where we're going? We saw this a couple of minutes ago, maybe 30 minutes ago. We have the terms, our second sequence, between -1 over n and +1 over n. Okay, but 1 over n, we know that goes to 0. -1 over n, that also goes to 0. Both -1 over n and plus +1 over n go to 0. And so our terms sine n over n also go to 0 by the squeeze theorem. Okay, so that's the second time that we are using the squeeze theorem in this video. All right, so that is our introduction to infinite sequences. Next time around, we'll talk about a different kind of infinite sequence called recursive sequences. And for those who don't have L'Hopital's rule or squeeze, I don't know, but there is a powerful theorem that will help us called the monotone convergence theorem. So until our next video, I hope you enjoy the rest of your day. Bye.